Good evening, and thank you for coming to this second public lecture by the Guyana Oil and Gas Association, Inc. This is our mode of delivering education to the public so that the conversation on the various topics and facets on the development of oil and gas can begin, and Guyanese can be fully aware of some of the issues that they need to understand in order to appreciate the benefits of an overwhelming oil and gas economy. And as we have heard last week, our resource is more than we had initially anticipated, and we are hoping that it will be even more in the coming years. Let me introduce the head table. With us we have Mr. Stuart Hughes, Director, Mr. Andrew Mendes, another Director of GOGA, and our feature speaker this evening, Mr. Brian McShane. In front of you, for those of you who collected the program, you can read a brief on Brian McShane. He's well-versed in the area of oil and gas development, subsea operation, and matters related to the development of what should be an effective oil and gas business.
Good night, everyone, and welcome to the second in the GOGA lecture series. As our previous lecturer last week, Mr. Kevin Ramnarine, the ex-energy minister from Trinidad, said, Guyana is essentially starting with a clean sheet in the development of this resource. Now, that clean sheet can either be a benefit because we get to start fresh and hopefully not make the mistakes of many of the other countries that we heard related to the previous lecture, or we can, because we start with a clean sheet and because we don't have the experience and we fail to listen to the experience of others, we fall into even greater pitfalls than other resource-rich countries. So, an integral part of this lecture series is really trying to wrap our heads around what is essentially a very, diverse and very complex industry. I know I've been part of a lot of discussions, even a training course for 4 days on oil and gas. And coming out of all of that, all I can say is how little I really know. And, I'm willing to admit that. So I think, part of this lecture series is really to try to broaden the awareness of what this resource brings, broaden the understanding of this industry a little to a wider population, so people can then start to make informed decisions. People can start holding wider discussions on where we, individually or collectively, how we can best benefit from this resource. So it's just to start this whole conversation, really, that we have started this lecture series to give a wider and broader understanding of the industry going forward. In reality, we have a very steep learning curve, and as I said, the more I learn about this industry, it seems that climb becomes steeper and steeper. All the things that have to be taken into account, all the issues that have to be addressed. What about local benefits? What about the Sovereign Wealth Fund? Just the technical names and all the descriptions in the industry is extremely hard to really wrap our heads around. Now, I know we had said at the previous lecture that we would look at doing 2 of these a month, but that may be a little much. We did take the opportunity because Mr. McShane was here in Guyana to have this lecture very quickly after the first one. But I would expect to see going on that there would be a little bit more of a gap between now and the next lecture. The idea is that through a wider discussion and sharing of ideas collectively and resources, both within Guyana and working with people in Guyana and also people from outside, because we have to accept that we don't necessarily have the expertise in country at the moment, that we can start to look at how we develop the capacity to take advantage of this resource. This may mean in future we talk about joint ventures, we talk about sharing resources with other people so that we can collectively benefit as much as we can from the resource. I know there's a lot of talk, it's all the way offshore, how much will we benefit? But we still do have a responsibility to ourselves and nationally to maximize what we can get in Guyana from this resource. And as I said, no one person or group is going to be able to monopolize this. This thing is just really too big. I think to the extent that we, work together collectively is to the extent that we can benefit from this resource. I know we're the cooperative republic, but I can only speak from personal experience in Guyana that we tend to honor that a little bit in the breach. Given the scope and scale of this resource, I think to really benefit, we will have to look at working together, forging partnerships, as I said, both within and without Guyana, so that we can all benefit collectively as much as we can from this resource. So without further ado, I'd like to hand over to Stuart to introduce our main speaker.
Thanks, Andrew. Good evening, ladies and gentlemen. My task this evening is to introduce our presenter, Mr. Brian McShane of INTECSEA. But before I do so, I just crave your indulgence for a minute or so while I put things perhaps into context as to why it's important that we understand about subsea operations in particular and the engineering that goes into the recovery of oil from reservoirs offshore in more general terms. As a nation, I think we have actually begun the process of trying to put in place the governance structures for our developing oil and gas industry. I think the Minister has said that he intends to table legislation in Parliament during the first quarter of this year related to a petroleum commission. I believe that they are currently preparing legislation on local content. In terms of transparency issues, I know Guyana is looking at becoming a member of EITI. In terms of developing a sustainable industry, we are looking at issues such as sovereign wealth funds, and there's a discussion that's taking place wider in the community and in the media, informed papers in our Sunday's newspapers. We're looking at perhaps infrastructure development funds so that we utilize the revenues coming from the industry in a sustainable manner. What I don't think has started as yet, however, is the discussion on the engineering and the operations of recovery of oil from the reservoir. And why this is important is because it's actually a very complicated science. Just going to give you an anecdote. When I first came back as a young engineer with a master's degree, I was really keen on sort of utilizing my knowledge in a specialized area of civil engineering. And one of our senior engineers, who I can say is in the audience, Mr. Bert Carter, had a chat with me, and he said, you know, Stuart, I know you come back with your big degree and thing, but civil engineering is really 90% common sense, 5% technical. And the other 5% is really magic because we don't really know why things actually do stand up. But there I was, all sort of excited about my specialized knowledge, and Engineer Carter said that it's essentially just common sense. What I can say, however, is that the engineering in the oil and gas sector is not common sense. It's actually a very complicated science which uses state-of-the-art technology. And it's important that we understand this technology for a couple of reasons, two of which are really key and important. The first one is understanding cost, because a lot of the cost is based on the technology employed. And my understanding of a production share agreement is that after you agree on your cost, it's the difference between your revenues and your cost, the margin, where you apply your various formulae for your production sharing. So we need to understand how it is we actually arrive at our costs. And that's where we need to, as a nation, as we engage with our partners, the operators and the supranationals, that we really understand the basic engineering of the cost structure of this industry. The second reason why it's important as well is a question of risk, and in particular environmental risks. the degradation, the damage that can be done from an oil spill in terms of destruction of our environment is fundamental. And in order to manage that risk, you really need to, again, understand the entire process, right from the reservoir, the wells, the wellheads, the risers to your FPSO, what an FPSO is, anchorage systems for your FPSOs, mooring, the entire chain right through, because unless you fully understand that, you can't really manage your risks. So it's very important as a nation that we actually do wrap our heads around the engineering and the science that goes into the production of oil. To help us do that this evening is Mr. Brian McShane. And Brian's bio is actually on the program, but I gather that not everyone has a program. So I will actually, unfortunately, go through and read this, even though I don't particularly want to, because I'm not very literate. And the older I get, I don't really see either. Anyway, Brian is a Senior Vice President for INTECSEA, Americas, responsible for all business aspects of the operations in Houston, Texas, and in Newfoundland, Canada. He is responsible for all consultancy, engineering, and execution support services associated with floating hulls, subsea, and pipeline systems. He has over 25 years of experience in engineering, construction, and project management of subsea, pipelines, and field developments within the oil and gas industry. Brian also has extensive experience in leading engineering and project execution programs for various offshore project developments and environments, including deep water, which is the case for Guyana, Arctic, environmentally sensitive, remote, and technically challenging areas. Brian has a strong background in technology and strives to implement the latest industry capability to ensure projects and enhance operational performance. Brian is well qualified. He has a diploma in engineering management from Bristol University, England, and a BA and an MA degree in engineering from Cambridge University, England. When I was a student eons ago in London, I had a friend who was at Cambridge who was also doing engineering. So after 3 years, we both graduated. I went on, did my master's. He went off, worked for a year. And then in a year's time, he, just as I was graduating, he actually said he was going back to Cambridge to get his MA. So I asked him, how on earth does that work? I mean, you were not actually under any formal education for the past year. He said, Stuart, my friend, if you pay £1, you can convert your BA to an MA. So I said, why is that? How is that? He said, Stuart, the level of engineering instruction at Cambridge is so advanced that BA is equal to an MA at any other university in the world. Brian, I just hope that you didn't pay your pung and got your MA. But anyway, ladies and gentlemen, without much further ado, I'd just like to invite Brian to come up to present what I expect will be a very informative presentation. And Brian, please, over to you.
Good evening, everybody. Welcome. Delighted you're all here, and thank you to the Guyana Oil and Gas Association for organising the gathering and lecture, and to all of you guys for coming out to listen to me. So I certainly appreciate you giving up your time and for the media to come out, and I hope I don't disappoint. So. But I'm here to share with you some things about Subsea, and very excited about that. You guys have got some great things going on here off the coast of Guyana, and so it's nice to be here to talk to you a little bit about what Subsea means around the world, how that has progressed in different parts of the world, and to share some of that knowledge with you. You'll notice my accent doesn't sound very Texan. I live in Texas, but I'm not actually from Texas. I'm kind of east of Texas, probably about 4,000 miles. I'm from Ireland originally, so I moved from a cold island to closer to a warmer island. And enjoy coming down here to visit you guys in the tropical area. So I appreciate the opportunity to speak to you. When I talked to Nigel and the team about lecturing, I said, I'm here. I'm happy to talk. Thinking I was going to talk to maybe 5 or 10 people, and they said, "Wow, do you mind if we open it up to the public?" And I said, "Sure, that's fine." And wow, what a turnout. That's fantastic. So excited you're all here. Hopefully you can hear me, and I'll talk through a number of things. I've shortened my presentation for tonight. Obviously it's an education focus, so I pressed it down, so we should be out of here in about 3 hours. Hopefully that's okay for you guys. And there's a quiz at the end, so hopefully that's going to work out okay. Now I'll talk for about 50 minutes or so, and then there'll be time for some questions. And really the idea tonight is really to give you a bit of an education around some of the jargon we use. Obviously every industry has its own jargon. What some of these things look like, general idea, give you a bit of a flavor of what happens around the world, and just to kind of give an overview of developments, and really focusing a little bit more on Subsea. And basically I'm just going to walk through a few slides and photographs. Ooh, powerful voice, and I'll try not to do that again, and just give you a real flavor of developments and where they all come from. So obviously you guys have seen this. This is the invite for tonight. Obviously we have a disclaimer. Basically this is the standard thing as part of our company. You probably have seen that. Obviously the expressions that I share with you tonight is really my opinions about things, but doesn't represent what our company's position is on some things. So that's just one of the disclaimers we add to all our presentations, as you probably see in this day and age. The print size is obviously set so you can all read that. And kind of focus on it. So I'm really going to focus on 4 key areas for you tonight. Hopefully you can see the presentation on the side, but just to give you an overview of projects and developments, some norms and some benchmarking for you. Then I thought it wouldn't be a bad idea to just give you a quick world tour of some projects. So I've selected 10 or so projects just from around the world, and just to kind of talk through what was special about it, what was unusual about it, because what you'll find is every location, every arena, every reservoir is a little bit different, and they all bring their different challenges. I'll then start talking through a little bit of the nomenclature that we use, and share that so you kind of start making connections between names and what that means and what it looks like. And then I'll just talk through some delivery challenges that we typically come across. So to start off, a little bit of history. It's interesting that everyone kind of wonders, well, how long's the offshore business been going? How long's hydrocarbons been going? So I just kind of put some key milestones. So kind of in the late 1800s was really when offshore started. And you can see here the first offshore well was in about 10 feet of water in the Grand Lake in Ohio. And then that moved to, during that same decade into Santa Barbara for the first saltwater channel. And you can see the photograph here is just the small derricks that were built out of wood. They were built on pylons in about 10 feet of water, and there was piers that were built out to these structures just to reach into the offshore market and offshore gas. 1920s, there was some more drilling. They started using concrete structures, and then obviously they started using floating and mobile drill ships in the 1930s. Interesting fact, obviously that's about production and wellheads. We started using pipelines to transmit and transport oil and hydrocarbon production. And actually during World War II, there was a development put in place that actually connected the UK to France. They reeled some diesel lines, and it was called the Pluto project. And that's really how reeling dawned. That's where you actually plastically deform a pipe around a spool, and then you unspool it again and lay it on the seabed. So that's where that kind of came from. And then obviously gradually as it progressed, it went out further and further offshore, and eventually we were going out of sight of land by the kind of mid-1940s, 1950s. That just gives you a bit of a flavor of the hydrocarbon business, the offshore business, and obviously since then it's been built upon many fold. These are a couple of graphics I use. You may not be able to see all these pictures and dots, but there's about two kind of benchmarking charts I want to share with you. One is around, what's the water depth that we built pipelines in. This is a very normal chart that's used, and it kind of looks at what's been achieved by the industry, and that's really the intent of this. So if you actually look at this chart here, you can see water depth on the side from 0 in meters all the way up here to about 4,000. And then diameter along the bottom. So this is 8-inch pipeline, around about 40-inch pipeline. And so there's a real correlation between what the industry's been able to achieve between the diameter of the pipeline and the water depths that it's actually been installed in. So two things that drive the what can be installed is what can you manufacture in the mills, and also what can these large vessels actually install offshore with their top tension. So if we show this plot, this shows what the industry's actually achieved. So you can see here there's pipelines being installed in 2,500 meters of water, that are in the 16-inch range. As you go into the larger diameter range, then the actual water depth they've installed in actually reduces, because it's all around the weight of the pipe and the tension that it lays off the back of the vessel. If you plotted this chronologically, you could actually draw lines here of how the industry's progressed from the top left to the bottom right, and gradually progressed out deeper and deeper, larger and larger. And for obviously the developments that you guys are looking at offshore here, you're in this region here, which is well within the industry capability and what can be installed from a pipeline perspective. So that's one example that I just showed to give you the idea of what's being installed by the industry worldwide. Another one I'll share with you is tieback distance. Now, what tieback distance is, it's a terminology. So where you have your reservoir and where you put your wellheads and trees, it's the distance from that location to where you're actually going to process the production. So obviously when production comes out of the reservoir, it's unprocessed. It may be three-phase, it may be gas, oil, water, mixture of various things. From that, where that comes and gets to the surface, it's the distance from that location to where it actually gets to the facility, the top side we call it, where it's processed. You separate the oil and gas, you separate the water, and so on and so forth. And this just gives you a flavor of how far from the subsea location you can actually reach back to in order to achieve that. So you can see here on the bottom, this is up to 80 miles here, and then this is the water depth from the top down, from 0 to actually 10,000 feet. And you'll notice in the oil and gas business, we flip back and forth from imperial to metric, depending on where you are in the world. That's just one of those things. Pipeline diameters are always in inches, for whatever reason, that's the norm. It is, in Europe, it's a little bit more in millimeters, but it seems to be, these are the metrics and norms that are actually used around the world. So, but just to give you a flavor, for gas subsea systems, there's been pipe developments that have been up to 90 miles away from where those trees are to where the production is actually processed. For oil, it's more in the 40-mile range. So that's the longest distance from that location. And here's another chart plotting the same information. And you can see here, apologies for that. Again, the red line showing kind of the gas reach is about 90 miles, and that's into about 2,000 meters of water. And the oil reach is into about 40 miles from that location of where the wellheads and trees are back to where you actually process it. So that's a pretty key metric, because that's some of the things that start to bind, okay, what does my solution look like, how am I going to develop this, and so on and so forth. So those are some benchmarking things I wanted to share with you, and just to kind of leave that with you. So we'll come back to that again, but if you can take away from here, that relationship between water depth and pipeline diameter, and also the tieback distance, that's pretty key to understanding how developments actually come together. So just to give you a world tour, I'm going to start in the Gulf of Mexico and head east, and we'll quickly get to, I think, as far as Australia, and then we'll stop. But we should be able to get to Australia in about 5 minutes, if that's okay. We're moving pretty quickly, but it should get there. So just to give you a couple of flavor of some projects in the Gulf of Mexico, Canyon Express was a development probably about 15 years ago now that was installed. And some interesting things you'll notice in the graphic here. So unfortunately, the seabed is not flat. So a lot of people think the seabed is, it's different kind of terrain, but the terrain in the seabed offshore is the same as the terrain on land. So you have to deal with the terrain issues, slope issues, so on and so forth. And you can see for this particular development, it was pretty challenging. The graphic, the kind of shading shows you the indication of the slope size and the scale, and some of the slopes that they were having to translate or traverse across were in the order of 20 degrees slope. Now, I think in somebody who's a skier will say that's equivalent to a black run, so that gives you an idea of kind of the scale of the gradient. But these are some of the challenges you face subsea. One of the other things about this development that was interesting is that it's really a combination of three fields, that each field independently couldn't have been developed on its own commercially, but when the partners got together and worked a solution together, then they were able to deliver a system configuration. The other thing that was very interesting about this is during the installation, is the installation vessel had to install the pipeline within 60 feet of the wellhead. Now, that may sound pretty straightforward, but when you think about it, the pipeline is being held from the surface on the vessel, which is probably a mile away from where the pipe is actually touching down on the seabed. So when you think of the logistics and the challenging and the survey of actually achieving that, it's actually very, very difficult to do, but can be done. So that's Canyon Express. CNG is another development in the Gulf of Mexico. The interesting thing about this development is, one of the things you'll see is that these hull shapes can vary. There's several different types out there. This one is a TLP development, which really is really trying to manage the motion, and it's really to do with what's the hull shape that can balance the payload that you're looking to hold up, and then also how your reservoir is actually spread out. This is actually a very vast and spread development, so there's several different reservoir locations. So this development was interesting in that it is now on its 10th expansion, and it ties back to the same hull. So the first one built about 3 or 4 locations where they drilled the reservoir and tied it back to the facility, and then over the lifetime they found more locations, drilled it, tied it back to the same location. So this is an ever-evolving opportunity that was built probably about 10 years ago now, so maybe a little bit further than that. So, and this is an oil and gas development in the Gulf of Mexico. And Stampede, this is one that's being built as we speak. Again, interesting thing about this development is it was actually high temperature, high pressure. So you'll hear us talk a lot about high temperature and high pressure, but what does that mean? We're talking about 250 degrees Fahrenheit is high temperature, and the pressure is in the order of 15,000 KSI, or 15,000 pounds or 15 KSI. So you can get a flavor of the kind of pressures, the size of the temperatures that you're dealing with. So very hot, very high pressure, and if you think of a couple of things, is the force that generates. It's pretty impressive. So pipelines move. They have to, your vessels have to be able to contain that kind of pressure. So you can see there's quite a few challenges in making that happen. Then we'll take a quick trip on over to another arena. This is now, we're moving into Arctic. I'll tell you a story about how I ended up being an Arctic engineer if you've got some time. But basically in the Barents Sea, there was a development that Gazprom was looking at called Stockman. It wasn't actually built. It was a number of partners actually, but this was a large gas play, which was large in scale in regard to the amount of gas it had to process. And also the arena. This was in an Arctic arena, so basically everything had to be qualified as cold temperature steel, which is a lot more challenging than you would think. So the steel had to still show ductility, fracture toughness at very low temperatures, sub-zero temperatures. So these were some of the challenges of actually coming up with a naval architecture solution for this hull shape that actually could withstand that kind of temperature and that kind of environment. So this is more of a hull challenge and a remoteness of location challenge than actually the subsea development challenge. So, but interesting project over in the Barents Sea. Moving into the Mediterranean, now you'll find in the Mediterranean it tends to be more gas plays. That tends to be where the type of hydrocarbon they find here. But there's 2 developments here. One was called Scarab Saffron, which ties back into Egypt, and I'll talk about another one in Tamar. Here's where a lot of groundbreaking technology really pushed the envelope on stretching the distance from that location of where the reservoir is back to where it's actually processed. And so this was the first one about 15 years ago that really pushed the envelope and got that tieback distance over 50 miles. It was actually up in the order of 60 miles. It also took on some challenges. Some of the challenges of long tieback distances is around the flow regime. So gas, we all think of it as a nice gaseous product, but often there's condensate with it, there's liquids with it, and how do you manage that when it's flowing through a pipeline system? It's also the other thing is how do you control everything remotely? So you're trying to control something that is that far away, and you have to have the control systems and the ability to actually function wellheads, function trees, and actually inject chemicals and so forth, and manage the whole development from there. So this is one of the ones that really started pushing the envelope on that distance. A subsequent one more recently is just off the coast of Israel. This is actually the record at the minute. It's at about 147 kilometers, about 90 miles, a little bit over 90 miles. And even in this solution, this one actually increase the capability of controls technology and move towards using fiber optics and elements like that to actually bring on the solution. So you can see if we're in this arena, the challenge is more long distance and how do you make the connection from where the reservoir is back to closer to shore. Some things that are happening in West Africa, there's a lot of development in Ghana. You can see in the Ghana region they're beginning to move into deeper water, 2,500 meters of water, taking on very high temperatures, high pressures. So and looking at what does the subsea architecture look like to pull that all together. But you can see the solution is a combination. They have a floating hull system with offloading system for the oil, and then obviously coming up with a subsea production layout that will access the different reservoir locations of where you want to place your wells, and also tie it all together so you can connect it all back into the hull. So the challenge here in this arena is it's kind of a developing hydrocarbon business. There is hydrocarbons in Ghana, but obviously this is then pushing it out into the deeper water, the high temperature and the high pressure, and then pulling it all together for the spread reservoir development. Jubilee again is a development in Ghana. This one was challenging. This one was the goal was to make it fast track and bring it on stream. So it used a lot of known technologies and they moved forward on kind of solutions that maybe the solution was a little bit more expensive, but it would definitely fit within the range of parameters of how it was going to be operated. So the drive about this development was to actually get it on from the asset find to actually make it in production in a very short order. And this one was actually came on within 30 months of the find. So extremely short development period, but that leverage kind of making very, there was less time to optimize the solution and really focus on, here, let's get a solution that's robust and actually can work. This is what they call a ship-shape hull, or an FPSO, and you can see all the top sides on it. Obviously below the surface is all the subsea equipment that tie back into this, and then this is where the process happens and then offloads and ships the oil back to market. Challenges in this arena was just really some of the architecture, so it came out, and I'll show you some examples of that. Just how do you tie it all together, very spread out reservoir, very challenging arena. And again, keep moving on, we're now in South China Sea, so we've made halfway around the world so far, only 5 minutes in. That's pretty fast. I think we're a little bit faster than Santa Claus, but we're making good progress. And here, this was the first subsea development in South China Sea. Again, what this one really strove to do was it still had to process the oil and gas, but you can see it leveraged the capability of putting the subsea equipment down the slope and tying back up this large slope here to a shallow water where you could actually put a rigid platform in. You could actually put a platform in the water depth that would connect rigid to the seabed, and that's a typically that's a little bit more economical than a floating system, but you can see they're leveraging subsea tieback technology and then obviously using the development processing point in shallower water. So, but again, you can see the South China Sea is moving into the subsea arena, and this was the first one that was built probably about 5 years ago. And I think the final one I'm going to show with you is Murphy, the SIGCAP. This again is in the Far East, and it's kind of showing here the subsea layout and how it ties it together. And I've got some examples that'll explain the different type of architectures and where they're named, but the idea is just to give you a flavour of kind of, you can see they all look a little bit different. You're kind of wondering what's different about it, and I'll talk you through some of the different solutions that were put together to make this happen. And I think finally, just in Western Australia, you can see here it's moving into the deep water. This is a fairly large hull. This would have been the first semi-submersible if it was built in this arena. And the interesting thing about this part of the world is, so we have hurricanes in the Gulf of Mexico and in the Caribbean area. Here they have cyclones, which are even at the next scale up in regard to environments and sea states and so on and so forth. So each part of the world has got different challenges. It's got different environments. Each part of the world's got different reservoirs. And so you can see that every single solution that you have to put together has to combine the industry capability, but it has to get customized for that development. So it's the world tour. We didn't make it all the way around the world, but we got pretty far. And hopefully that gives you a flavour of kind of some of these developments actually look like. So the big question on your mind, and you're trying to process this and think about it, is so you can see the developments They usually have some kind of floating hull. They usually have some kind of subsea architecture. And the question is, well, how do you go from a blank canvas to then saying, this is my answer? You know, what's the process to get there? How do you do it? And it's a number of different features. And, you know, that's the other 3-hour part of the lecture that I'm not going to show tonight. But as you can imagine, the first thing you got to know is you got to know what's in the reservoir. So you have to shoot your seismic, you have to drill some exploratory wells, and then you got to figure out, have I got oil, have I got gas, have I got a combination, do I have water, you know, and then where are the different locations of where this reservoir sits? Is it all in one location? Is it 10 kilometers over here, 20 kilometers over here, 30 over here? And where is it relative to the beach? Where is it relative to the infrastructure? Where is it relative to how I'm going to take, because at the end of the day, this is just getting the production out of the ground. You still have to get it to market. You still have to find out, okay, where is my market? What kind of market am I selling to? Am I selling gas? Am I selling oil? You know, how much production do I have to deal with? So you have a lot to think about. And just to kind of give you, just to reorient you a little bit. So you first got to look at, okay, where's the find? How far offshore is it? Is it oil? Is it gas? So for example, if I had an oil find and I'm 100 miles offshore, maybe further, we know that, well, the subsea piece can only go about 30 to 40 miles back to where that rises to before I have to start processing it. So if you're 100 miles offshore, you suddenly go, okay, I need a facility close to that reservoir because I can't tie the reservoir all the way back to the beach. So that's kind of one conclusion. And then you start thinking through, okay, now I've got that, what type of subsea development do I need? So I'll kind of walk through, I'll probably skip this one because I've covered a lot of this. You start thinking about, okay, what drives my subsea solution? And you start asking yourself questions, well, how many wells are there? You know, where do the wells need to be? Is it all in one location? Is it spread across several locations? And then the other thing is so now how am I going to tie that back to where I need to process it? And then how am I going to get that to market? So you can see all these questions start flowing through, and actually the field architecture and defining the solution, this is probably the hardest piece of actually developing a solution, is taking all the stakeholders, all the different pieces that impact the outcome, and putting it all together to come up with the best solution. So we just kind of walk through, I kind of showed you various flavors of these, but I'm going to explain what they are. So the simplest one in the subsea space is a single well tieback. So this is pretty straightforward. You have one location, one well here that you install, and then you have to connect it back to some kind of host facility or platform. So it's called a single well tieback. But you can see the infrastructure is pretty simple. You have a subsea tree, you have it connects over here to a structure, and then it ties back through a flow line to the platform. And then this umbilical is what manages the controls. So then you start getting a little bit more complicated, and you look at well template manifold. Now here I've got 3 wells to install, but I want to be pretty efficient at how I do it. So I'm going to drill through a template, which is a structural orientation guide that I use to drill with. And then I'm going to stick all my trees on top of that manages and controls the reservoir and the well. So you can see here you've got 3 wellheads and trees on top, and then I've connected these over to the flow lines, and then I tie it back. So that's a well template manifold. So you can see what drives that is, how am I going to drill my wells? How am I going to construct my field? How am I going to tie it together? So you can see everything's pretty close together, pretty neat, and pretty straightforward. But then you start looking at a manifold cluster. Now here, I'm using a slightly different drilling technique in regard to, I'm not going to drill through a template, I'm going to drill kind of independently from that, but I'm going to drill my wells close enough together that I can set them all up, and then I'll connect them into this structure called a manifold, and then I'll connect it back into the flow lines that take it back to the processing facility. So again, and again, you can go on, then it starts getting more complicated. Here I'm putting the wells further away from where that structure gathering, this gathering structure is called a manifold. I'm putting it further away from that location. This distance can be in the order of 10 meters or 10 kilometers or so. So that might be where you've got a very spread out reservoir and you need to access all these locations. And then there's other things where you can daisy chain. So this is where you connect, you've heard of parallel and series in the electric world. So daisy chain is like connecting things in series. You can see I've got one wellhead here in 3, I connect it to the next one, but they're all flowing through the same flow line back to my floating facility here, and then it's offloading into this tanker. So you can gradually see these are some of the terms we use and how you piece together the different so the components you're using are the same. It's just the plumbing's a little bit different and the structure's a little bit different, but it's all around trying to deliver the right answer to get access to the reservoir to maximize the recovery of the production. So I've given you an idea of some projects. I've given you a flavor of some of the different architectures. And I know I've worked through a lot of these things very, very quickly. I know you won't remember all of them. But it hopefully gives you a bit of a flavor of some of the terminology we use and some of the jargon we use. It starts getting quite complicated, particularly around these control systems as all the different pieces of equipment that you need. And you have got to remember is we're in 6,000 feet of water, 2,000 meters, right? No human being is installing this. This is installed by remotely controlled vehicles. Okay, so you're working on trying to visualize with obviously the video, and then you're using torque tools and structural and mechanical arms to actually install this. So you've got to think about effectively robots installing this, and you've got to think through the process of how that works, because you don't get the same, when we're actually doing something as a person, we get a reaction from touch, whereas you don't get that same sensation when you're actually using an automated system to install that. So you have to think about these kind of things when you're actually designing equipment. So that gives you a flavor. So now you know everything. So now for the pop quiz before I go into the final thing. So no takers. Okay. So but hopefully that gives you an idea of the technology, a bit of a flavor of some of the terminology, and just kind of how these things are fit together. Just to just another rule of thumb. So we talk about 6,000 feet of water. What does that really mean? Okay. So the metric on land that I think of is the Empire State Building. Empire State Building is 1,250 feet, 1,250 feet, okay? So we're about 5 times the height of the Empire State Building, from the top of the water to the seabed. That's the kind of scale of the arena that we're working in. The other thing to bear in mind is the pressure in about 6,000 feet of water, is at about 3,000 psi. That's the hydrostatic pressure in that water depth. So you get an idea of the scale of the forces we're dealing with and the scale of just the engineering and the size of the equipment that has to be installed to withstand that pressure. So just to give you a flavor of delivery challenges, I like this picture. It kind of shows you a little schematic, and it varies. But things you need to be worried about is weather. Every region has a different environmental regime. Water depth, obviously, the deeper the water, the larger the vessels you need to install it typically. Tieback distance, we talked about that. That's the distance from where the wellheads are back to where the production facility is. And then obviously what you have in your reservoir is very important as well. Is it oil? Is it gas? So this is the most unexciting picture I have. It's all text. Sorry about that. I couldn't get it. I thought I'd put it in just to see if you were paying attention. But basically, if you think about delivery challenges, you have to think about the arena. So environment, location, remoteness, reservoir. What do you have? And then you have to pick out of what solutions do I need for my flow line, for my risers. Risers, I didn't talk about that. Riser is effectively the vertical section of the pipe that connects the flow line on the seabed to the floating facility. So that's another terminology that I didn't go through. We talked about architecture, and then what floating system. Is it a ship-shaped hull? Is it a TLP, a tensile leg platform, so on and so forth. And then you've got to procure it, fabricate it, and install it. So these are all similar challenges you have in most projects, even projects you build on land. You have these kind of things. What's the solution look like? What am I going to use? How am I going to buy it? How am I going to build it? How am I going to operate it? So weather, very interesting, but part of the thing is figuring out what is our weather. So the weather ability is getting very sophisticated as the currents we can measure, the rainfall we can predict, the waves that we can do, the hindcasting. So because we design for extremes, we design for the extreme event, not the day-to-day stuff. We design to survive the extreme event. So it's very important to get this kind of data to drive your facility. This is one of my favorite pictures. This was taken in the Gulf of Mexico maybe 3 years ago, but it's rare that you see something like this, but this is actually 4 hulls that were being designed, built, and deployed all at the same time, and they're all different types. So, but the point here is for your facility or your development, you need to pick out which hull form that works best for you. So for example, we have what they call tension leg platforms. So this is a hull structure here. You can see it's got 4 columns. And why it's called tension leg is that the mooring system is a vertical component that is kept under tension and then holds that facility in location. So the thing about that is it doesn't have a lot of heave motion and it doesn't sway very much. So this means that the vessel motions are fairly reduced, which is attractive for many different ways, about your riser systems and so on. So that's one. So this is the Olympus hull that was installed about 2 years ago, 3 years ago, I think. Give you an idea of height. This is about 65 meters in height. So what's that? A 20-story building, something like that. Gives you, So, and then this is a Bigfoot. Here was another TLP hull. This one here in the middle is a spar. So this is a long cylinder. So the vessel motion. This moves more like an inverted pendulum. So it kind of bolts around like this. So it has a different set of motions and a different water depth that it can actually be deployed in. And then the one in the far corner is a semi-submersible. This is not dissimilar to what you'll see drill rigs look like a lot of the time, but this typically has a much larger payload for a heavier topsides. So it usually can carry a heavier topsides. Again, it tends to move a little bit more, so it's got more vessel motion challenges. But again, all are feasible solutions and all are being used in the offshore market. What I didn't show you here is obviously the ship-shape hull, which is obviously more what the FPSO, floating production offloading system. Maybe there's probably more of them deployed around the world than any of these ships together. So, but that's all part of your decision: is what type of production do I have? How do I need to offload the production? What does it look like? And then flow assurance. We talked about flow assurance. Finishing up here in a couple of minutes. Flow assurance, really this is a study of the internal hydraulics or the reservoir production fluids. And it's got to do with a lot of issues of, do I have oil, do I have gas? But this has usually got a mix of all sorts of things in it. And some of the things you have to figure out, and you may have a challenge, you may not. But things like slugging. So basically there's a fluid regime where you have a block of liquid, and then you have a block of gas behind it, and so it flows through like a big slug of liquid, and it can have some energy behind it. And that's not a good regime of flow that really kind of maximizes the throughput of the system. We have hybrids here. This is where when you mix gas and water, you form ice effectively under pressure, and so you get a solid block of ice. So you want to make sure you stay away from that type of phenomena. Corrosion, all various forms of things, waxes, emulsions, all sorts of things. So you can see there's a lot of study goes on about, do I need to keep this fluid hot? Do I need to manage it? Do I need to put some internal cleaning tool through the system to keep the annulus open for flow? So it's very complicated and lots of hard work done here. Riser system I talked about. These are just some of the different flavors of riser system, and really it's around how do you connect from the seabed up to the floating facility. So we have things like steel continued risers. These are free-hanging pieces of pipe, effectively, in a catenary or a catenary. I can never remember which way to say it because I've lived in too many different parts of the world. But you can see it's just a free suspended pipeline system. Very compliant. So when you think of it as a structural engineer, so some of the systems we've installed, this suspended length is probably in the order of 10,000 feet or maybe 2 miles. So you can get the idea of the scale of some of this stuff. Here you have a vertical tower that's supported by a buoyancy. This is like a hybrid riser system, and then it's connected through some kind of vertical piece of pipe, flexible piece of pipe. And then this one here is a flexible composite, which is another type of riser system you can use. Procurement, buying equipment, figuring out what you need to buy, managing all that, getting the delivery. Obviously another challenge, but obviously very doable in the market, in the industry. And then installation, the scale of the vessels you need to hire. This is just some of the different things you need to have. So to install these jumpers, you need to have some kind of lift crane and spreader bar. To install pipelines, you may need a fairly large vessel to install some of that. And this here is a compressor spread that actually is increasing pressure to actually sweep the water, because typically what you call your hydro test the pipeline systems once you've built them, and that's just to pressure test it, but then you have to get the water out of the system, and this is just some of the equipment used to take that out. So there you go. So that's the first R of the 4R series. But that's really all I had to share. So it's kind of very high level, just kind of talking through some of the elements of Subsea and how it all fits together. So before I finish, I'll take some questions. But for you guys, I think you're in a very exciting arena. Delighted to be here to talk to you, and I think the opportunity is there for the taking. I think my encouraging words would be collaboration. I think the projects that have been the most successful is when all the key stakeholders have all collaborated together to get a great outcome. And so I think you guys are having all the right kind of conversations to make that happen. I encourage you to do so. So thank you for your time, and I appreciate it. I'm happy to take any questions.
Tell me something about the operation of the robots. The robots have a mind of their own, or they operate from the mind of their own?
No, so when I put the presentation together, I suddenly realized that I didn't show a picture of an ROV. So operated vehicles, the terminology is an ROV, and basically it is a unit that has a large buoyancy piece on the top, because obviously you need something to keep it neutrally buoyant, and then it has all its drives, so it's got a series of propellers at the back, and then at the front it has mechanical arms, and the mechanical arms are operated remotely from the vessel that sits over the top of it, and they can pick tools out of their tool bag. The tools are specifically designed for different ports that you stab into. So in some cases the tool rotates, and so it'll spindle a valve and rotate it in one direction. Other tools are used to pressure sense. So there's just there's various tools that are used, and so these vehicles can switch out the connection point at the end of the arm and then stab into the different point on the piece of equipment.
What's the margin of a robot making a mistake?
So they're all driven by. So even though they're robots, they're driven by people. So there's usually a series of protocols that go in, and so there's a series of tests before you actually operate or function it. So for example, the first thing one of these robots will do is usually you'll see their grab points on the equipment. So the first arm will grab to hold its position, and so it's continually streaming the data from that location. The next thing is it will then use its arm that it's stabbing into the port, and then it can test the connection. Okay, so it tests that the connection is good. So there's a series of protocols to go through that before you take the next step, you confirm that the last step that you've done is correct. So I don't think I can really comment on the margin of error, but there's a lot of structure and protocol and rigor put in place to function and operate these units to really make them work. Thank you.
You're in the abyssal plane, essentially. You may not have that great amount of topography, seafloor topography. What do you think would be the cost of, say, 50 wells?
Varies, right? There's unit cost per different piece of equipment. But ranges, the subsea equipment, depending on the scale, can be anywhere install costs from $500 million to $1 billion, maybe more, depending on just the scale, the size. But typically, a lot of times, the more wells you have, the more it'll be a phase development. But then the host facility is also a pretty expensive facility. We've seen facility costs anywhere from $2 billion, $3 billion. It just depends. It depends the scale and size of the unit and how much production you're going to push through it, and just how many wells and production is tying into it. But it's in that kind of range to give you a flavor. So
you have had any trouble, say, with turbidity currents in these deep sea environments?
So one of the things that's a lot of time spent on it is maybe not turbidity clearance. Loop currents is quite commonplace. There's no challenge with them. You just have to understand what you have. So For example, in the Gulf of Mexico, some of the loop currents on the surface get up to 4 knots. So it gets pretty significant, and when they come into the Gulf, they tend to stay for 3, 4, 5, 6 weeks. I think the ones that you have here in this region tend to pass through very quickly. So I think the environment around here is well within the arena of where the industry has been successful in delivering projects before. So I think for you guys, I think it's really a capability.
I live in St. John's, Newfoundland, on the east coast of Canada, where we have a combination of subsea developments and developments from fixed platforms. We have 2 big concrete platforms, and we have 3 FPSOs, excuse me, current in production. So my first question is, at what stage does an operator, an oil company, decide to go with a floating system and therefore a much more complex and robust subsea system rather than a fixed platform? My second question relates to the evolution of subsea. I've been fortunate to spend a lot of time in Norway over the years, and in Norway these days they're doing more subsea than ever. For instance, when the oil comes up from the reservoir, as you pointed out, it's a mixture of oil, gas, water, maybe sulfur, and it comes up to the platform, and the whole purpose, of course, of an FPSO or a floating platform is to separate the oil from the gas and either re-inject and store and transport. But I noticed some of the more recent developments in Norway, they're doing it all subsea.
Typically the breakover point for that is really in around the 500 feet arena. Once you start going deeper than 500 feet, rigid structures become very cost prohibitive because you're moving them into a very large arena. And so that was really, as the industry discovered oil in deeper water, subsea has evolved to meet that need. There was a couple of platforms built that are in the 1,200 feet range, and they were probably the largest platform structures ever built. These are huge, huge developments. But, those will never be built again because subsea technology has evolved. So my rule of thumb is around 500 feet is the breakover point, where you can see the cost efficiency start moving, that a subsea solution is much more effective. In regard to subsea technology, so what Rob's referring to is, can we do more of this processing on the seabed rather than taking the free-phase fluids back to some kind of facility and then process there? So that has been an evolving story, and some of the solutions are subsea pumping, so effectively taking these fluids and putting them through some kind of subsea pump to increase the pressure and ship it. There's also subsea separation. So I think those different technologies are at different levels of evolution. The one that's maybe been most tried and tested is the subsea pumping. The next one on the list is subsea compression, subsea separation, but they're still, I would say, at their infancy. So I would say there's still a bit of ways to go. And that's something that we monitor from an operations perspective, just where the technology is on that. One of the biggest challenges of actually going that direction is not the equipment, it's not, those have got their own challenges, but it's actually power supply. These units, like a subsea pump, takes 5 megawatts to run. So if you start putting all these units in, your actual power supply becomes very significant. And then you start running into the challenges of power transmission. So if you're trying to transmit several, watts of power across long distances, you need to be able to transmit a very high voltage. And so there's limitations on what you can do with that. So those are some of the things that are going to affect the development and the evolution of the equipment. We're not there yet, but I think there's certainly a drive to do that. But I think it's going to be a journey.
I just wanted to know the end process. This is all very new to me. If a company was to close out an operation, what is the process involved? What is the process involved? How are all that equipment? It's very extensive. What is the process of removing and those sorts of things? Well, if a company like Exxon and so on were to about they're here, but what would they have in place?
And so it depends on the arena of where it is. It depends. That's there are some standard approaches on that. So typically on wells, they call it plug and abandonment.
So typically you'll plug cement out the well and take the tree off it. So from the surface, from the seabed, you won't actually see that there actually is a hole drilled beneath that. So that's kind of closed out. In some cases, some other structures are removed, depending on where you are in the world. Sometimes it's actually more difficult and more dangerous to remove the structure from the seabed than it is to make it inert, if you will, and then leave it there. So, because one of the things that's interesting about these developments is, for example, flow lines, they actually create environments for life forms to exist. So if you think of a pipeline flowing with a certain heat to it, you can find, what you find is that we find that fishermen start fishing at these locations. So putting this equipment on the seabed can actually create life form and habitats for environments. So a lot of the time it's an assessment around is there a habitat there that's nurturing something that maybe you want to leave, and so therefore you just want to make the system inert so it's not going to be corrosive or anything like that. And other times you say, well, maybe it's better that we remove that piece of equipment. Typically our experience is that it tends to be better to leave it where it is and just make it inert to the environment. So for example, the flow lines, you would sweep all the hydrocarbon out of it, you would put nitrogen in there, and you would leave it inert to the environment. That's a fairly common approach to leaving these in place. There's different parts of the world have a rigs to reefs program. They really use, so maybe 30 years ago, some of the rig developments were actually left in place and made habitats for environments. So it just depends where you are, it depends what the environment is. So there's no one solution for your question. But it's really but that whole development, part of the assessment through that process and operating it is to think about what do you do at the end of life. In regard to capex, so deep water developments as a unit, so there's two things that drive cost per barrel of oil. One is how much oil do you have, and the other one is how much capital are you going to spend to recover that? Because there's different ways you can recover production. I can say I want to get it out over 10 years, or I want to produce it over 20 years. So the duration affects, obviously, that capital investment and the scale and size of the facility that you build. So it's really, those are the two components. Typically, deep water is more on the higher end of cost per barrel to make it cost effective. I've seen a graphic floating around that's showing deep water ranges for cost efficiency in the range anywhere from $70 to $100. It's in that grade, but it depends. It all depends on your development. It depends on how much production you have. But there's no one answer to that. So I'm probably not the right person to answer that question. But if you want to look at ranges, it's in that kind of range. So.
Would it be fair to say then, as you said, that basically the whole design and the effort you put in up front can generally reduce the overall cost of it, the more design you have in it. So ideally then the more time, as you said, they rushed in Ghana to put it into operation, and that would have ended up being a higher cost operation, correct?
The development that was looked at more at getting a production quickly, so there wasn't as much information known about the field, so the structure, the system was more robust, if you will, and so, but it turns out it was a pretty effective and efficient solution. But it's just a different approach to the development. But I think your point is that a good understanding up front helps, but also if you can enhance the recovery and the amount of barrels you recover, then obviously that improves the economics of the whole situation. The rigor and standardization control and safety is pretty significant in the energy sector. Every small, if there's even a small amount of chemicals spilled on the deck of a vessel, it's captured in the drains that are there and it's reported. So there's a lot of rigor around how the energy sector operates and moves forward.
That's on the surface now.
Obviously, we had this event. It was a kind of conglomeration of a number of different issues. But since then, maybe I talked to you moving forward. There has been a lot of development in the blowout protection technology that's used. There's more redundancy in that, and there's also a program, you may have heard of it. There's a response solution which has all the equipment on the beach ready to go that will allow you to cap a well and shut it in. So there's been a lot more development on having equipment readily available, and a lot of time during exploration is that strategy and that response is already part of the planning for the actual exploration well and the production wells. So that planning of what is my contingency, where does my equipment sit, how do I stage it, how do I get access to it, that's all part of that whole development process before you even start drilling. So there's a lot more backup redundancy approaches, equipment in place to provide that there, if there was ever another event of that scale. My belief, my experience working around the world is to be successful, you have to collaborate. And that means all the stakeholders who are involved have to be willing to collaborate, and they have to be realistic. And so that would be my encouragement for you guys, is that, as you go forward and work together to get these solutions in place, obviously there's wins for everybody, but what that looks like and what success looks like, you guys are going to have to work together to figure that out. So, my encouragement is just be really collaborative and just very positive and just embrace the opportunity.
I'm kind of taking them back to in the pace in which our oil and gas industry is moving, in which the second session of the Guyana Oil and Gas Association is already the hardware for extraction. we are moving very, very fast here. And my concern is the best practices in the industry. For example, all the different scenarios of your extraction or production that I've seen there, I'm wondering how much collaboration there is with companies like yours in the regulatory agency of our country, and I see their representatives here, and those executive advisors in the environment, as to whether or not we will use one system against another, considering not only cost, because at the pace I'm seeing this is moving, I think that certain things can be compromised. Because you just said a year and something to install that thing, and we're talking about oil in 2020.
So all that I share with you is proven technology. It's all those different solutions that I shared with you have all been built before. The equipment's all being utilized on other reservoirs, same pressure or higher pressure, so they're qualified and are tested to that level. So the equipment, that's basically the discussion is more around how many of the pieces do you need, where do they need to be located, and how does it tie together. So that's kind of one of the topics. So hopefully that gives you a little bit of comfort that the equipment's being used is very proven technology. In regard to moving at a quick pace, obviously, the environmental impact is part of the assessment of the development, and so I think that's going on at the minute. And so that's obviously being taken into consideration as one of the stakeholders in the whole process. So I'm not sure I'm answering your question, but hopefully I'm giving you some comfort that the equipment's tested, these solutions have been delivered before, it's well within the industry sweet spot. And that was the benchmarking graphs that I was trying to show you, that if you actually plot the opportunity here across what the industry's achieved, it's well within the sweet spot. And I think the other thing to be aware of is for the different elements, there aren't that many vendors who actually produce those elements. And so basically, there's a lot of very strong equipment suppliers who sit in that arena, who have delivered this equipment all around the world. And so they're very recognized and very, very known entities.
Thank you very much for an interesting overview of the industry in a short period of time. My question is, there's a lot of expectation, given the fact that Guyana has no support infrastructure, that there will be infrastructure coming from probably Trinidad. Given that Trinidad is not deep water, such deep water, is that translatable? Can Trinidad provide the support, or will it come from further ashore from the Gulf of Mexico?
So the question is, for a deep water arena, which this is, if the solution can't come from Guyana for whatever reason, is Trinidad still ready to meet that need? So let me talk to something. So some of this, the hardware that I showed you, would not, there's only a few locations in the world that we manufacture anyway. Those are international products that are made in certain areas, so there'll be equipment coming from certain places. The installation vessels that you use are international vessels as well, typically, because of the scale of them. So some of these vessels, if you will, they're, some of the heavy lift vessels are, the deck is like three times the size of a football field. So that gives you an idea of the scale of that. So there only are so many of those kind of assets in the world anyway, right? So a lot of the, just by definition, there's certain suppliers and providers that they're the ones who can do that. In regard to the other elements, so Trinidad has fabricated subsea manifolds before, so that is a capability that sits there. They have done other elements of fabrication, so there are assembly things that have been done. They've been supporting the drilling the same way you guys are deep water drilling here. So there are experiences there that are available that aren't too far away that can support that. But the whole thing, that whole how you're going to deliver it is all part of the execution strategy planning, and that'll be a key part of the overall program. So hopefully that's answered your question to some extent, but gives you a bit of an idea of where we're at.
Thank you very much, Brian. I think our sectional lecture hosted by GOGA is quite different from the first. It's a bit more technical, but thank you, audience, for the very pertinent questions. I know some of it we cannot answer it at this forum, at this presentation, but they are all very key questions towards the development of the oil and gas sector. Brian, we want to thank you very much for this lecture. I think it opened the audience's mind and the wider Guyana when it's broadcast into the media of what subsea operation is. The conversation on subsea will start tomorrow, I know for sure, if not when persons leave this room. Stuart also mentioned that there are some measures that are being put in place by the government, and we cannot lose focus of that. Things are being done that we read in the media, so we're thankful for that as well. But a key aspect of what we want to deliver on some of these lectures are getting to know the science and the technical aspect of oil and gas development. The business of oil and gas development might be known by many, close people such as our neighbors in Trinidad and Suriname, to a lesser extent Venezuela, but we're not going to use that example. So that is known, but understanding the mechanics of oil and gas development is something which we want to start to talk about, and this presentation today was initial start of understanding the science and the technical aspect of oil and gas development. The engineering science is key. At our presentation last week, we did, our key presenter there did speak about not just understanding petroleum law or petroleum economics, but also understanding the technical aspect of it and getting the science involved in oil and gas so that people can see opportunities that are involved in such areas. Brian, you opened up our minds to topics and terms such as tieback distance, subsea tree, which I don't think we ever really spoke about that much in Guyana. But it's good that you give us a world tour of offshore development, so we have an idea of what offshore development should look like, and maybe what ours will look like in the next 5 years or so. And what are the subsea development and the options for subsea development in the deep water that we have here. And of course their delivery challenge, which I think some of the questions asked, but we know that there are much more challenges in developing a subsea operation. So on behalf of the executives of GOGA, the directors who are present at the head table, and those who are in the audience, Nigel, Suresh, Anand, John, and Alan and Philip, we want to thank you very much for being here. We know that the room was a bit too small. We also want to thank you for the overwhelming support that you've given to GOGA's first lecture. We will have much more activities within the year, but as our consultant Rob indicated, at the end of March, we're going to have a major oil and gas conference, one that we want to put at an international standard, and we hope to have much more discussions on this. The 4 areas that Rob indicated are also areas of opportunities for Guyanese to learn and understand how oil and gas will be developed over the next 5 to 10 years or so.